Hello again, physics friends. Today we are going to focus on the two postulates of relativity. And what I mean by that is that all of special relativity is derived from two underlying principles. Those two underlying principles are the so-called principle of relativity, and the second is the constancy of the speed of light. Now, we've already seen the second one when we talked about the relativity of simultaneity, and we're going to come back again and talk in more detail and show some experimental evidence that supports the second postulate. Today, though, in this video, we're going to focus on the principle of relativity. When we say that a theory like relativity has two underlying postulates, what I mean by that basically is if you imagine, you kind of sketch this out graphically, if you have special relativity, almost like a structure. So you have this structure of special relativity, and it's built on two main pillars. Okay, and those two main pillars are these two postulates. Okay, so the supporting pillar number one would be the principle of relativity, and the second is that the speed of light is a constant. Okay, and I don't know, maybe this is like Stonehenge, right? It's sitting on the ground and there's grass growing here. And this theory of relativity is fine and will survive as long as both of these pillars are intact. Okay. If we in the future do some experiment and find a violation of this second principle, that maybe in certain reference frames the speed of light is not 1 foot per nanosecond, or maybe there is some frame dependence to physics theories, and we'll explain that more in a minute, then that would kind of put a crack in one of these pillars. And the consequence of that crack would be that the theory of special relativity would not be pristine. It would also suffer the consequence of a violation of Law 1 and Law 2, because these two postulates, number 1 and 2, are the basic assumptions that go in. They're the starting point for the derivation of the consequences in special relativity. In the readings and the class notes, I give several different ways of framing the principle of relativity. Here's one. Okay, it's quite verbose, but I'll read it out. No experiment that we can do can enable us to distinguish between our being in a state of rest or a state of uniform motion. So that first part of this paragraph is really the core. Any set of experiments we perform in a laboratory we choose to regard as stationary must give exactly the same results as a corresponding set of experiments done in a laboratory that's moving uniformly with respect to the first one. And here's another way of saying essentially the same thing. All other things being equal, it doesn't matter how fast you're moving as long as you're moving at a constant speed in a straight line. One reason I like this way of saying is that it gets rid of a lot of the jargon, a lot of the terminology. If you wanted to introduce some terminology, we could recognize the fact that constant speed in a straight line is another way of saying constant velocity, and is also equivalent to saying uniform motion. Okay. So let's see this principle of relativity in action. Okay, so imagine you have the ground, and we'll have a train car, and we're going to put Alice on the train car. Okay. So here's Alice on a train car. This train has wheels, and she has some box, and inside this box she's running an experiment. Okay. And she does the experiment and she measures an outcome. And while she's doing this, the train is at rest relative to the ground. Well, the claim of the principle of relativity is that if she does exactly the same experiment, but this time the train is moving relative to the ground at a constant velocity, straight line motion at a constant speed, then she's going to get the same outcome in her experiment. So from her point of view, if she was in this train car and there were no windows, everything was blacked out, she couldn't see the outside world, she would have no way of determining if her train was at rest relative to the ground or was moving at a constant velocity relative to the ground. The experiment would have the same outcome in both cases, and in fact, any experiment that she could envision would have the same outcome in both cases, and therefore she has no way of determining the first scenario from the second. Is she moving relative to the ground, or is she not moving relative to the ground? Now, of course, the assumption of a constant velocity, we have to take that really seriously. That means there's no bumps in the road. She's not jiggling up and down or wiggling in her seat as the train is kind of rumbling along the tracks. We are really talking about perfectly smooth motion at a constant speed in a straight line. And part of the reason that some students have some challenges with this idea is that it's almost never in our lives are we moving at constant velocity, truly constant velocity, right? If you're in a car, you feel the bumps in the road, you can kind of tell you're moving because you're getting accelerated by those bumps. So there's a few cases, and you might have experienced one, and I'd love to hear about it, where you've actually been moving essentially at a constant velocity. And you may have had the sensation of not being able to tell actually if you were at rest relative to the earth or moving. And that is a very bizarre and quite unique sensation. In fact, a good operational definition of the of uniform motion is to use your kind of biological accelerometers that are built into your body. Your body's really good at sensing acceleration, okay? You feel it in your stomach when you're in a car and you crest a hill or you're riding a roller coaster. You can kind of feel that sinking or rising feeling in your stomach. You feel it in a sense of dizziness when you spin around. You have the tubes in your ears in which fluid is flowing to identify rotational motion. And you can feel it when you're in a car accelerating or decelerating, slowing up or speeding down, because you feel pushed into the seat or thrown forward from your seat. Or if you're in a car that's taking a tight turn, you feel pushed into the wall or the side of your car, or pushed towards the middle of your car, depending which direction you're turning as you're making that trip. Okay, so that feeling of acceleration or a feeling of turning is your body telling you that you're accelerating. And acceleration is not uniform motion. So if you want to keep something in your mind about what it means to be in uniform motion, it's when you do not have any of those sensations of acceleration, none of those biological feelings of acceleration. That is one way to think about uniform motion. Well, so the next question is, and a natural next question is, does the principle of relativity apply to non-uniform motion or motion that's accelerated? And that one is very straightforward to answer. No, it does not. Okay? And it won't take you long to think of an example where you can tell the difference between being at rest and being in an accelerating frame. And we've already kind of talked about several examples, right? If you are in a car and you feel yourself being pushed into the seat, that is different than the experience you have when your car is parked in a driveway, right? So that feeling of acceleration allows you to distinguish between accelerated motion and uniform motion or being at rest. Okay. Another example is, if you were to, I kind of do this sometimes when my kids are in the car, right? If you're parked in your driveway and you're pouring water into a cup, that water is going to go right into the cup. But if your dad accelerates rapidly while you're trying to pour water, then that water will end up in your lap instead of in the cup, or maybe on your shirt. So there are actual experiments that you can do to distinguish between accelerated motion and uniform motion. And the principle of relativity only applies to uniform motion, constant velocity motion. There's a fancy term that we give for uniform motion, or a reference frame that's moving uniformly. That term is inertial frame. And an inertial frame is simply a reference frame that is in uniform motion. So that black and white video called Reference Frames that you watched earlier in the week, in that video, when you couldn't tell whether the first guy or the second guy was the one moving relative to the ground, that was because they were both in inertial frames. They were both in uniform motion, either at rest relative to the ground or moving at a constant velocity relative to the ground. Okay. So if you're in an inertial frame, you have an absence of this feeling of acceleration. So an inertial frame is a non-accelerated frame. Okay. A lot of times students say, well, okay, how do I know if I'm in an inertial frame. So imagine you are in a rocket ship, no windows, can't look outside. What's at your disposal? What tests can you do to determine if you are in an inertial frame or not in an inertial frame? Well, here's maybe the most simple test that you can do to tell if you are in an inertial frame or not. Okay? Take an object, put it down at rest on a tabletop. So you have a stationary object. Does it stay at rest or does it begin moving? Okay? If that object stays at rest when there's no explicit applied force on it, okay? So if the answer to this question is yes, then that means you're in an inertial frame. Inertial reference frame, IRF. If the answer to that is no, then you are not in an inertial reference frame, okay? And so what are some examples of situations where the answer would be yes? Well, how about a parked car? Okay, if you put a ball on a flat tabletop in a parked car, it's just going to stay at rest. The ball will not roll either direction. However, if you do the same thing in a car that's speeding up, then that ball will start to roll, even though there's no force acting on the ball. The same would happen if your car was turning in a circle. Even if your speed was the same, 60 miles an hour driving in a circle, that ball would roll on the tabletop. That's indicating that a car that's turning or making a car that's turning in a circle or any other curve is not an inertial frame. However, if you're driving at 60 miles per hour on a flat road, and there's really no bumps on the road, then that ball would stay still on the table, and that would represent an inertial frame. So a parked car or a car moving in a straight line at constant speed, those are both inertial reference frames. A car that's in the act of changing speed, speeding up or slowing down, or one that's turning in a circle is not an inertial frame. So I'll close with one more slide. And on this slide, I want to talk about how you can use and misuse the principle of relativity. In other words, what is the principle of relativity saying and what is it not saying? Okay. One thing that it's definitely not saying is that the measurement of a quantity that you make is independent of your speed. Okay, that is not what the statement is saying. So let's see how we would how this might be used incorrectly. Okay. So let's say we have Alice standing on the ground at rest, and she's measuring the speed of a ball that's coming towards her. She's going to measure that speed. Now, what happens though if Alice starts moving towards the right? So we'll put Alice on a skateboard, and Alice is now moving to the right. Is she going to measure the same speed for that ball? No, she's going to measure a speed that's higher, because we're going to find that the speed of the ball relative to Alice is going to be actually, in this case, the sum of her speed and the ball's speed. Right, remember from the non-relativistic velocity addition, we have this expression. But even just by looking at the picture, right, if she's standing still, then the only speed she measures is the red arrow lengths, the velocity of the ball relative to the ground. But if she's approaching the ball, then the gap between her and the ball is closing faster than it would have been just due to the motion of the ball alone. So she's going to measure a higher speed for the ball. So it's completely incorrect to say that the outcome of her measurement is independent of her speed. That's not what the principle of relativity is saying. The principle of relativity is saying is that all objects that are relevant in the measurement have to be moving uniformly in order for the outcome of the experiment to stay the same. So how would that look? To use the principle of relativity correctly, we have to group the ball and Alice as a unit, and then we can translate that whole system, and what we'll know is that Alice will measure the same speed for the ball in both cases. So what I've drawn here is Alice and the ball approaching her, just like I did in the first picture above. What comes next, though, is that now we take that whole setup, everything in the purple box, and we move that whole setup to the right at constant speed and constant velocity. And then we can say correctly that Alice is going to measure the same speed of the ball in the second case as she would have measured in this first case. Okay, so you need to not only translate the person, but you have to translate the ball. You have to translate everything that's part of the measurement. Now, this example maybe seems a little weird to you, that you could translate everything, even the Earth, but actually we're doing that all the time, right? Like when we say we measure the speed of the ball to be 5 meters per second, we're not accounting for the fact that the Earth is barreling through space as it travels through the solar system, and we're not accounting for the fact that the solar system is barreling through space as it travels through the galaxy, and let alone the motion of the galaxy. All of those motions do not affect the measurement of the speed of the ball, at least not in any appreciable way. Right? The caveat to that statement is that, as you know, the Earth is not moving in a perfect straight line. It's in a circular or roughly circular orbit around the sun. And we had said before that circular orbits represent non-inertial frames. So how is it that we can say the Earth is an inertial frame? Well, it's definitely true that over the course of a year, the Earth moves in roughly a circle. But for short periods of time, our motion is very, very much straight line, constant speed motion. So we are very close to being in an inertial frame, even though we are not exactly in an inertial frame. For the purposes of this course, we are going to assume that when we say Earth frame, we mean inertial frame. And in fact, all of the work that we'll do with special relativity in this course will involve inertial frames. Frames that are either at rest relative to something or moving at constant speed relative to another inertial frame. And constant velocity, I should say, not just constant speed. For those of you interested, there are definitely ways to detect the fact that we are in a non-inertial frame. If you have a sensitive enough apparatus, you can do so. Some of you may have heard of Foucault pendulums or seen one in action, and that's a pendulum where the pendulum swings back and forth, but the plane of that swinging motion rotates over the course of the day as the Earth rotates on its axis once per day in 24 hours. So there are ways to detect the fact that we are in a non-inertial frame due to the rotation of the Earth primarily. But those, you need very sensitive experiments running for long periods of time to see that, or you need large-scale systems. So if you're sending a ballistic missile a substantial distance along the Earth, the trajectory of that projectile will be affected by the rotation of the Earth. And similarly, hurricanes and typhoons, their direction of rotation is determined by the fact that we are in a non-inertial frame of a rotating Earth. Those interesting complexities and add-ons, though, I'm going to put aside for now. And like I said a few moments ago, for this course, we're going to focus entirely on inertial frames. There will be no acceleration, and all of the motion will be one-dimensional. So in that case, we're restricting our focus to quite straightforward phenomena in which there's left-right motion, say, or up-down motion, say, but not both at the same time, and we're not going to be changing speeds. We'll have uniform motion, constant velocity. So that wraps up this presentation about the principle of relativity. In the next video, we're going to come back to the second item on the list of two postulates and focus on the speed of light. And I'll say a few words about why we believe the statement that the speed of light is constant independent of reference frame.